Okay, hi everyone. Welcome to Organic Chemistry 2, and we're going to start with chapter 10. Okay, so in this chapter, we're going to learn about reactions of alcohols, ethers, epoxides, amines, and sulfur containing compounds. Okay, okay, so you have learned about alkyl halides in Organic Chemistry 1. And in alkyl halide also you have a electron withdrawing group, which is a halogen group. Halides are your halogens. They are your fluorides, chlorides, bromides and iodides. Okay. And in this family, we call it as group 2 family in this book. So all the families in group 2 have an electronegative atom or group attached to an sp3 carbon. Now let's look at here alcohol OH group, alcohol attached to a R group. R we call it as an alkyl group. Okay, and this alkyl group is sp3 hybridized. If you remember from general chemistry 1, okay, you might remember that if you have a carbon and then you have 4 hydrogens attached to it like that, what is the hybridization of this carbon? It has 4 electron groups, which are your single bonds, and we call this carbon is sp3 hybridized. So alcohol group OH is, this is OH attached to sp3 hybridized carbon, and this is a ether functional group. In an ether you have oxygen, and oxygen is flanked by 2 alkyl groups, and that is a ether functional group. And then we also going to learn about reactivities of epoxides. Epoxide is a 3-membered ring like that, where you have oxygen. Now it is a cyclic ether. You see here, alkyl, oxygen, alkyl. Here also it is a ether, but it is a cyclic ether. We call it as a epoxide. Okay. And then we also going to learn about quaternary ammonium hydroxides. That's an amine group. And then we're going to learn about sulfonate ester. So this is called sulfonate ester. It has a sulfur in the middle. And then also sulfonium ion. Sulfonium ion is sulfur with 3 alkyl groups. So we're going to learn about reactivities of these groups in this chapter. Okay. And their reactivity depend on the basicity of the leaving group. And see, these are the pK values of these leaving groups. Alkyl halide. Halides are fluorides, chloride, bromides, iodides. They are negative 10 to 3.2. Alcohols negative 15. Ethers negative 15. Sulfonate ester negative 6. Amines 40. Quaternary ammonium ion negative 10. Sulfonium ion negative 6. So the pKa of conjugate acid of the leaving group also determines how good it as a leaving group. Basically the basicity. Okay. Now we are going to do some reactions of alcohols. But the alcohol OH group is a very poor leaving group, meaning OH group doesn't want to leave as a hydroxide group because it's a very strong base. Okay, because of that we want an acid to convert this poor leaving group to a good leaving group. So methyl alcohol, which is a strongly basic leaving group, if you add a nucleophile like Br minus, a reaction will not take place. Okay, because hydroxide is a strong base. So what happened, let's say if this reaction happened, so since hydroxide is a stronger base compared to bromide, so the hydroxide will go and attack again the methyl group and leave bromide. So this reaction will not take place. So then what we normally do is we are converting this poor leaving group to a better leaving group. So instead of using Br minus, now we can perform the reaction in an acidic medium. HBr is now hydrobromic acid. So what's happening here? Hydroxide group goes and take a proton from the acid, and then it would become oxygen with two hydrogens. And then when oxygen will have two hydrogens, it would become positively charged. It's a hydronium ion right there, methyl hydronium ion. Now this hydroxide that you have, it is a strongly basic. Now we have converted it to a weakly basic leaving group. Now between hydroxide and water, which one is a stronger base? OH minus is a stronger base. Now this is going to leave as a water, which is a weak base. Now one hydrogen is removed from HBr, so you have Br minus left over. So now bromide can attack the methyl group and then leave the water molecule, become methyl bromide. Normally, if you want to eliminate hydroxyl group, what we do is we're going to protonate it with acid, make it a good leaving group, and then we can do the reaction. We call this process as activation. Alcohols must be activated before they can react. Only weakly basic nucleophiles can be used. Strongly basic nucleophiles will react with the proton. Converting alcohols into alkyl halides. Now this is a primary alcohol. In the presence of hydrogen iodide, we can heat it up. This triangle means it's heating. So the substitution takes place. Hydroxyl group will substitute for iodide group. So now you have propyl iodide. That's a primary alcohol. And then if you have a secondary alcohol in the presence of hydrobromic acid, again this will protonate and make it a leaving group, good leaving group. So it can give you bromocyclohexane. And if you have a tertiary alcohol, again in the presence of hydrobromic acid, it can form a tertiary bromide. Primary and secondary alcohols require heat, but the tertiary alcohol does not require heat, because the tertiary carbocation that forms is more stable compared to primary and secondary. Now here's the mechanism, the reaction of secondary and tertiary alcohols with hydrogen halides, and they are SN1 reactions. Do you guys remember the SN1 reaction? That is the unimolecular nucleophilic substitution reaction. Okay, so what's happening first? Again, so we are going to substitute this OH group with bromide. Remember, this is a poor leaving group because hydroxide is a strong base. First, we have to protonate. The acid protonates the most basic atom, which is the most basic one. So you grab a proton, arrow pushing takes place, lone pairs of the oxygen goes and take this hydrogen. The bond between the hydrogen and the bromine breaks. Hydrogen will go to this oxygen. Now oxygen will be positively charged because it has 3 bonds on it, making it a good leaving group. Okay, now once this protonated water molecule is been formed over here, this can leave by itself. It doesn't need any other help because the resulting cation is a tertiary carbocation. You see, we have learned in the Organic Chemistry 1 the stability of the carbocations. Tertiary carbocation is more stable because of the hyperconjugation from the 3 methyl groups. Okay, so once the water molecule falls off, nucleophile bromide attack the carbocation center, reaction of the carbocation with a nucleophile. So the bromide forms the bond with the carbon, and then you can form the substitution product. Okay. An elimination product can also take place once the carbocation forms. There are 3 methyl groups, and so the bromide can act as a base and grab a proton from any of these carbons, one of these hydrogen, and then it can form alkene product, which is the elimination product. Okay, so you can have substitution product as well as elimination product. Reaction of primary alcohols with hydrogen halides are SN2 reactions. Now the previous one, which is a tertiary alcohol, which is SN1 reaction, now this one is SN2 reaction. So this is a primary alcohol. And you have hydrogen bromide. Again, the first thing is the protonation of the alcohol forms a good leaving group. And then the bromide, now since this is a primary alcohol, it is SN2, the 2 molecules involved in the rate determining step, bimolecular nuclear substitution. So bromide goes and attacks the carbon, and then it leaves the water molecule. It forms the substituted product. Now it is a primary alkyl halide. Bromide is a good nucleophile in a protic solvent. So bromide is a good nucleophile. Alcohols undergo SN1 reactions unless they would have to form a primary carbocation. Now the chloride. Remember in the previous slides it was the bromide that was the nucleophile. And chloride also one of the halogens. But compared to the bromide, chloride is a poor nucleophile. Because of that, it needs a catalyst. Chloride is the poorest nucleophile of the halide ion, so it needs a catalyst. So what's happening here? What we want to do is we want to substitute the alcohol group with the halogen chloride. Okay. And we can do it in the presence of the zinc chloride. Zinc chloride is the halogen. Zinc chloride increases the rate of the reaction by creating a better leaving group than water. So what is happening here? Again, OH group is right there, and it's going to attack the zinc, and chlorine leaves. So by doing this, oxygen is making a bond with zinc. Oxygen making a bond with zinc, and one of the chlorine is attached like this, and then the other chlorine left. So the left chlorine, it's going to leave as Cl minus ion with the 2 electrons from the bond, and now it can participate in SN2 reaction. Chloride attack the carbon and leaves this zinc chloride hydroxide complex. So it makes a better leaving group. It was hydroxyl to begin with. Now it made a good leaving group so that the poor nucleophile chloride can attack the carbon and can leave this group. Okay, and then we have the substituted product.